did his undergraduate at Williams College, right? Will, did I catch that
Yeah.
right?
Yep. Yeah.
Yeah. And you've been at Tufts for just a few years, joining Peter Love's research group on quantum computing, and already author or lead author and co-author on a few papers that I'm aware of, maybe more. Very active already in quantum computing, and we're looking forward to having him as our speaker today. So without further ado, Will, please take it away. And may I ask others to mute their microphone if they're not speaking, as I will now do myself.
Well, thanks so much for inviting me. I'm going to see, here we go, good. So you all can see my screen and hear me?
Yes, both. We can
Great.
hear you and see your screen.
Yeah, well, thanks for inviting me to talk to you. This is fun because I've been working with some of you on these high energy physics simulation projects, and this is the work that I'll tell you about today is kind of the other half, if you will, of what I've been working on in Peter's group. So I'm excited to get to share it with you. So as Jim said, I'm Will Kirby. I'm a grad student of Peter Love, who's listed here. And Andrew Tranter is the third author in some of the later work that I'll talk about. He was Peter's postdoc, and now he's working at Cambridge Quantum Computing. Good. So first of all, I will go over some general background of quantum computing, just to make sure that we're all on the same page. Then I'll talk briefly about quantum simulation, my work with some of you on simulating high energy physics is a subset of this. And then I'll talk about VQE, variational quantum eigensolver, which is a particular type of quantum algorithm for quantum simulation that's appropriate for using on the kinds of small scale noisy quantum computers that we have now. And then I'll get into talking about our work. I'm going to be giving you an overview of actually 3 papers. So I'm going to be presenting sort of main results without going too far into the nitty-gritty of proofs, just to try to give an overview of this collection of work that we've done. So in this first part here, I will talk about this notion called contextuality. Contextuality is a feature of quantum mechanics that distinguishes it from classical mechanics. So it's a kind of non-classicality. And I'll talk about how we can identify contextuality in the setting of variational quantum eigensolvers. Then in this next section, I will talk about what it means for a Hamiltonian and a VQE instance when the Hamiltonian is non-contextual, which is the classical case. So we should expect this to mean that the Hamiltonian is more classical in some sense that we'll define. And then finally, I will talk about what we can do in the case when the Hamiltonian is contextual. So the contextual case is the full quantum case. And what we're going to end up doing is developing a hybrid quantum classical simulation algorithm where we split the Hamiltonian up into a non-contextual part that we simulate classically and a contextual part that we simulate on the quantum computer. And the part that we're going to end up simulating on the quantum computer requires fewer qubits, so less memory, and fewer measurements as well than the original VQE would. Okay, so first of all, let's do a quick overview of quantum computing. So in analogy to a classical computer, we can define a quantum computer as follows. A classical computer, first we'll talk about memory. So in your classical computer, like phone, laptop, or supercomputer, the basic memory components are bits, which are 2-state systems. So we can label their states abstractly as 0, 1. And an analogy to this, on a quantum computer, the basic computational component is a qubit, which is a 2-level quantum system, like a spin 1/2 particle or a photon. and sometimes they're built in other ways. But a quantum system with 2 levels, so we can think of this abstractly as just being normalized complex linear combinations of the 2 classical states. So we take the classical states and we promote them to be basis vectors, and then we take those to be the basis for our quantum state space. So if we now generalize this to n bits, the classical computer memory ends up being represented as length n bit strings, where each bit is just the state of the corresponding 2-state system in memory. And on the quantum computer, we can think of this as, again, just taking the classical states to be the basis for the complex state space. So we have complex normalized linear combinations of length n bit strings for n qubits. So for example, if we have a quantum computer with 3 qubits, I did mean to say, I guess, yeah, there's 2 to the n bit strings of length n. So that's the dimension of our Hilbert space for n qubits. So if we have 3 qubits, 2 to the n is 8, 2 to the 3 is 8. So we have the 8 possible length 3 bit strings as the basis for our Hilbert space. So now we've talked about what the memory looks like. But in order to do some computation, we have to do some transformations in memory. And we know that the allowed time evolutions in quantum mechanics are unitary operations. So in principle, we can perform any unitary operation to transform the state of our quantum computer, as long as the unitary operation is of the correct dimension. So for example, on our small quantum computer with just 3 qubits, the possible operations are going to be 8 by 8 unitaries. And I may often refer to the unitary operations that we perform as gates, which is just jargon borrowed from computer science. And finally, at the end of our computation, we need to read out some information. So we know that we're not allowed to just look at a quantum state directly. And what we can do instead is perform certain measurements. And it turns out that for quantum computing, it's usually enough to assume that just at the end of the computation, we're going to measure in this 0-1 basis, which we sometimes call the computational basis. So measuring each qubit in the 0-1 basis is the same as projecting onto the bit string basis for n qubits. And so we get outcome B with probability given by its coefficient magnitude squared. And that's just the same as the Born rule. So let's look at a quick example of a quantum circuit. This would not be a particularly useful thing to do with a quantum computer, but it's good for illustration. Suppose we want to generate a truly random bit, just one. Well, it turns out that we just need a quantum computer that has 1 qubit for this task. So our basis is just 0 and 1. And the algorithm works like this. First, we prepare some state that's easy physically to prepare on the quantum computer. And we usually assume that this computational basis, the 2 states 0 and 1, are chosen to correspond to some physically simple states. So they might be energy levels of whatever system we're using. Like say it's a spin 1/2 particle with in a magnetic field. So we prepare anyway one of these computational basis states, and we can label that as a vector like this. And then we apply this unitary operation. This is called a Hadamard gate. It's one of the often one of the basic operations that we assume that we can perform on the quantum computer. In a lot of architectures, something that looks pretty much like this operation is relatively simple to physically perform. So, and if you check, it's not too hard to see that this is unitary. So when we apply this matrix to the vector 1, 0, we just pull out the first column of the matrix, which looks like this. And if we translate that back into a vector, or in terms of kets, we can see that it's just the uniform superposition of the kets 0 and 1. And now finally, at the end, we're going to measure in this original computational basis again. And so if we project this state psi1 onto that basis, we find that the probability of each outcome is just 0.5, the coefficient squared. And so if we've done all of the pieces of this algorithm, ideally, then we get each outcome with exactly probability 1/2. So we've generated a perfect random bit. So these are the general, this is just to give a flavor for what the general pattern of a quantum algorithm may look like. And as the last piece of my background, this is going to seem like a little bit of a non sequitur, but we're going to be using them all over the place shortly. I need to introduce the Pauli operators. So a n-qubit Pauli operator is just a tensor product of single qubit Pauli matrices. So we know and love the Pauli matrices, which act on two-level systems, and a qubit is just a two-level system. So if I have n qubits, then I can make tensor products of the Pauli matrices to generate an n-qubit operator. So here we have sigma x, sigma y, sigma z, and 2x2 identity. And I'm going to be typically abbreviating these as just capital letters and dropping the tensor product symbol. So I would change this long expression to this shorter expression. And the salient facts about Pauli operators for us are going to be first that they are Hermitian, so they're observables, and they have eigenvalues ±1, which means that they're self-inverse, because if we multiply a Pauli operator by itself, then all of the eigenvalues become +1. And they form a basis for the Hermitian operators, at least the ones of the appropriate dimension, those on n qubits. So we can write any Hermitian operator, any observable, as a linear combination of Pauli operators. And they either commute or anti-commute. And this is going to be kind of one of the key properties for us. If you remember, the single qubit Pauli matrices, sigma x, sigma y, and sigma z, all anti-commute. But when we take tensor products of them, they could also commute. And it turns out that if they commute, then their product is itself a Pauli up to a sign. And so for example, these two operators turn out to commute, and we can see that because on the first qubit, so x and y are the two pieces on the first qubit, they anti-commute. On the second qubit, they also are x and y, so they anti-commute again. So if we were to switch the order of this Pauli operator and this Pauli operator, then we would pick up two factors of -1. And then on the third qubit, they're both z, so they commute. And on the fourth qubit, we have identity and x, so they commute. So overall, we're going to pick up two factors of -1 if we swap the order of these, so they would commute. And if we work out what their product is, we have x times y is iz, imaginary number I times z. X times y is imaginary number I times z again, so we have an overall factor of -1. Z times z is identity, because the Pauli operators are self-inverse. Pauli matrices are self-inverse. And I times x is x. So we end up with z, tensor I, tensor x, and an overall factor of -1. Any questions about this so far?
Will, let me make sure we're following your notation here. So in the bottom line here,
Yeah.
The first entry within each parenthesis signifies what you're doing for the first qubit.
That's right.
Now, it's implicit, I guess, in your notation that you have 4 qubits in the system.
That's correct. Yeah.
Or is this qubits numbers 1 through 4 of an arbitrary number of qubits?
It could be that, and then we would have implicitly have like extra tensor factors of the identity.
Okay.
But really, I'm talking about 4 qubits here. Yeah.
Okay.
Yeah.
Good. I want to make sure I'm following.
Yeah, perfect. So I'm this notation here on the left is, yeah, a little bit cheating, because some of the products are tensor products. Inside the parentheses, the products are tensor products, but between the two parentheses is just a regular matrix product. So that's clear over here.
Right. And up till now, you're only talking about single qubit operations stitched together, if you like, in a sequence. You don't have yet any operations which involve simultaneously 2 or more qubits, right?
Well, it's kind of up to you how to think about one of these single qubit, or sorry, these Pauli operators. So for example, this first one, x, tensor z, tensor I could think of that as, well, it is unitary. I'm going to be thinking of them more. Pauli operators are both unitary and Hermitian, so we can think of them as transformations or as observables. We're going to be thinking of them more as observables. And so this is, yeah, you can think of it as a product observable. So it's kind of independent actions on each qubit, but it would pick up correlations between, how to say, this whole operator, if we were to measure this as an observable, will just have a single outcome plus or minus 1 for the eigenvalue of this whole operator. So we shouldn't think of this as measuring x on the first qubit and then measuring x on the second qubit and then measuring z on the third qubit and then measuring I on the fourth qubit.
Okay, maybe I could pose my question a little bit differently.
Okay.
Are all possible operations you have in mind expressible in terms of Pauli matrices and identity matrices? Well, identity is one of the Pauli matrices.
Yes.
I mean, okay.
So we're going to be using Pauli operators to decompose observables.
Right.
So things that we want to measure, observables that we want to measure in some state. Right. And every observable can be written as some linear combination. So shortly, we're going to be talking about Hamiltonians. Maybe this slide answers your question, the next slide. But we're going to be looking at Hamiltonians that are written as linear combinations of Pauli operators. And we are always going to be writing them as linear combinations of Pauli operators.
Yeah, I guess the point you're making is that for qubit space, for a space of qubits, the unitary operations are spanned by the set of Pauli operators, and so everything should be expressible in terms of the SU2 algebra, if you like, represented by the Pauli spin matrices.
Exactly. Exactly. And I'll talk about this a bit more in this slide and the next one. But that's exactly right. Yeah. Okay. So that's basically it for the general background. Now let's talk briefly about algorithms for quantum simulation. This is an important type of quantum algorithm because it's one of the kinds of quantum algorithm where we're pretty sure that we can get an advantage over classical computation once the quantum computers are big enough and we have a good enough handle on the noise. And the reason for that is just that we know that quantum simulation algorithms for simulating other quantum mechanical systems can be made efficient in the system size. And although to my knowledge, it's not been proven, there are no known classical algorithms for simulating general quantum mechanical time evolution that's efficient in the system size. So what we're usually going to mean by quantum simulation, there are some exceptions to this, but it usually means we're simulating some Hamiltonian. And that could either mean we're simulating time evolution of a state under that Hamiltonian, or we're trying to calculate some of the spectrum, which usually means low energy states. And in a lot of cases, just means that we're trying to find the ground state energy of some Hamiltonian. And as I'm sure you know, the ground state energy is useful for a tremendously wide variety of tasks in quantum chemistry, quantum field theory, condensed matter. So I don't want to try to go and list those because it would take the rest of the time to talk about applications for the ground state energy. Oops. But just as an example, if we have, here's an example of a possible 2-qubit Hamiltonian. So we can tell that it's 2 qubits because each of these terms here is a tensor product of 2 Pauli matrices. So again, this is just like sigma z tensor 2 by 2 identity, and so forth. And so this is going to be a 4 by 4 matrix. So we should expect it to have 4 eigenvalues, and this is what they turn out to be. And this is actually one of the examples. This was an early being only a few years ago, example of a Hamiltonian that was actually simulated on a quantum computer. So very small kind of toy example, but they were trying to approximate the lowest ground state energy, which is this number. And the algorithm that they were actually using in that paper is this one. So now we're specializing even a bit further to talk about the variational quantum eigensolver, or VQE. So VQE is mostly just for the purpose of finding ground state energies. There are modifications you can do to try to find excited energies, but generally, when we're talking about VQE, we're trying to find ground state energies. So this algorithm also is probably the leading algorithm for approximating ground state energies on existing quantum computers. And the reason for that is going to be that it doesn't require the quantum computer to maintain coherence for very long compared to other algorithms. So it's suitable for the kinds of noisy machines that we have now. So like above, we're going to assume that we're given some Hamiltonian that we're interested in, H. And as our pre-processing step, we need to cast this Hamiltonian as a qubit Hamiltonian, which for the purpose of VQE, we're just going to assume means we're going to cast it as a linear combination of Pauli operators. And there are various known transformations for doing this, depending on what kind of Hamiltonian you start with. But for example, if it's a fermionic Hamiltonian, you could use Jordan-Wigner transformation or the Bravik-Kitaev transformation to change the fermionic ladder operators over into Pauli operators. And I should note that this isn't the only choice. This is the one place where I'm going to talk about other kinds of decompositions. It is possible to translate Hamiltonian into a qubit Hamiltonian under some other decomposition that's not Pauli operators. But Pauli operators are the standard method for VQE. So then once we have this form, for the algorithm itself, the main process runs on the classical computer. And that classical process is just to minimize the energy or the energy expectation value as a function of some parameters that we can denote theta. And this involves repeatedly evaluating the energy for different values of the parameters and applying some classical optimization scheme to try to minimize the expected energy. And then given this classical optimization loop, the part that runs on the quantum computer is just the actual evaluation of the expected energy for a given parameter setting. And the way we would do that is we first prepare some state by applying some short quantum circuit that I'm denoting by U of theta that's a function of the parameters. So this generates an ansatz state, psi of theta. And then we measure the value of just one of the Pauli terms in the Hamiltonian, so some p. So this p is the set, this set of Pauli terms in the Hamiltonian is S. So we measure one of these p, we're going to get an outcome plus minus 1, because those are the eigenvalues of the Pauli operators. And then I just repeat that over and over again, this preparation and then measurement, until I've done enough measurements to estimate the expectation value of the term p to whatever my desired precision is. And then I just repeat that for all of the different terms in the Hamiltonian. And because the expectation value is linear, I can then just take those individual expectation values for the terms and add them up in linear combination to get the expectation value for the full Hamiltonian. And so that is going to be the input to my classical optimization procedure. So this is good for noisy quantum computers, as I said before, because this circuit U can generally be chosen to be short compared with other kinds of quantum algorithms. And measuring Pauli operators turns out to be a fairly simple thing to do on quantum computers. And that's the only piece of this that actually needs to happen on the quantum computers, just this repeated preparation and then measurement. Okay, how am I doing on time? Good. So yeah, let me ask if there's questions, more questions at this point. I'm now going to get into talking about our work. Okay, great. So we want in quantum computing generally to try to identify quantum advantage over classical computing. This is a major goal of the field. And what that means is that we just want to identify types of problems that are classically difficult but can be solved efficiently on quantum computers. And as I was saying before, we think that simulating other quantum mechanical systems is such a problem, but proofs of this kind of quantum advantage are generally quite hard. So as a step in that direction, we're going to think about how to identify intrinsic quantumness in the problems themselves. In other words, we want to try to identify what separates this VQE algorithm for some Hamiltonian from a classical algorithm that might try to mimic it. And we're going to focus on the set of measurements, this set S, which is just a set of Pauli operators, because this is the part of the algorithm that is actually run on the quantum computer, is measuring the terms in S. So we want a means for identifying intrinsic quantumness in some sense that we'll define in this set S of Pauli terms in the Hamiltonian. Okay, so now we get to introduce this idea of contextuality, which I mentioned at the beginning. So to get into thinking about this, suppose S, this S is some set of Pauli operators that are the terms in the Hamiltonian. Suppose we want to construct a realistic hidden variable model for S. And this will be a model in which we could classically interpret all of the observables as having real actual values at all times and interpret the probabilities that we would get from the Born rule and uncertainty relations as just restrictions on our knowledge of the real actual values of the observables. So suppose we want to try to construct such a model. This model would be essentially classical. So if we can successfully construct one, then that will mean that our set S of Pauli terms is essentially classical in some sense as well. So this model is going to consist of two pieces, which I've already kind of alluded to. First of all, we're going to have some set of joint value assignments to the operators in S. So this just means we're going to assign plus minus 1 to each of them. And we can think of these as something like phase space points for the model. So in the classical realistic interpretation, as I said, these would correspond to the real actual values of the observables. And then the second piece of the model is some set of allowed probability distributions over the joint value assignments. And we would interpret these as representing our state of knowledge of the actual values of the observables. So implicitly included in this set of probability distributions will be some uncertainty relation, which would apply in the case when S does not fully commute. And that's just going to restrict our possible joint knowledge of observables that might not commute. So let's look at a quick example. Suppose we just have, these are the single qubit Pauli x, y, and z, so sigma x, sigma y, and sigma z. Well, the possible joint value assignments are just the 8 possible assignments of eigenvalues plus minus 1 to x, y, and z. And then the possible probability distributions over these we can visualize, I think most easily with this picture. So in this picture, we've got a cube, and we should interpret the corners of the cube as probability 1, the points representing probability 1 for each of the possible joint value assignments. So for example, this would be probability 1 of the outcome assignment plus 1, plus 1, plus 1. And it turns out that if we draw this picture, the set of physically allowed states meaning the actually allowed probability distributions, looks like a sphere that's inscribed within this cube. And we can see the uncertainty relation reflected in the fact that this sphere prevents us from getting too close to any of the corners or any of the edges, because if we could actually reach the corners or the edges, that would represent knowing the values, having certainty in the values of 2 or 3 of these operators at a time, and these operators don't commute. So we know that that's not physically possible. But again, we're interpreting this restriction as a restriction on what we as the observer are allowed to know, rather than as the restriction on physical reality. So this finally brings us to a qualitative definition of contextuality. So this set S is contextual if it's impossible to build a model of this kind. And you'll notice that that's not quite the definition I have here, but for Pauli operators, it will turn out that if it's possible to set up the joint value assignments in a self-consistent way, it will also be possible to construct the probability distributions. So in fact, we can restrict our attention to just looking at whether it's possible to construct joint value assignments given some arbitrary set S in this self-consistent way. Okay. So I'm talking about consistency of joint value assignments. So what would it mean for a joint value assignment to be inconsistent? Well, we want our classical model to give the same predictions as quantum mechanics for the set S. And one such prediction is that commuting observables are simultaneously measurable. So any commuting subset of S is simultaneously measurable. So if we're interpreting, we want to be able to interpret the assigned values to S as real classical values for the observables, which means that if I measure some commuting pair PQ in S, which I can do simultaneously since they commute, then from the values that I will get, which are the assigned, must be just the assigned values, I can infer the value that's assigned to their product PQ. So for example, if my set were just single qubit X acting on each of a pair of qubits, so this is X tensor I and I tensor X, then for any of the 4 possible assignments of plus minus 1s to these, I can infer the value to their product X tensor X. And I can visualize that with a little diagram like this, where the leaves are the operators in my original set, and the parent node is the product of its commuting children. So this we would refer to as an inference, a single inference. So we're given an assignment of values to these, we can infer an assignment of value, the value of the parent node in this tree. So here is a slightly more technical definition of contextuality now, and this is going to be the one that we actually work with, which is that S is contextual if and only if any joint value assignment necessarily violates some inference relation of this kind. So let's see an example of how that can happen. Suppose S contains single qubit Pauli X acting on each of a pair of qubits and single qubit Pauli Z acting on each of a pair of qubits. Well, if we have some value assignment to these, what additional operators can we infer values for? Well, it turns out that there's 4 commuting pairs here, and we find these 4 pairs in the bottom layer of these 2 trees. So for example, Zi commutes with Iz, so we can infer the value of the product ZZ. But once we've inferred the values for these 4 products, ZZ, XX, ZX, and XZ, we can notice that ZZ actually commutes with XX and ZX commutes with XZ. Why is that true? Well, this is Z tensor Z, X tensor X. So if I were to transform ZZ times XX into XX times ZZ, then each of the single qubit pieces of that anti-commutes. So I'll pick up 2 factors of -1 when I do that switch of order, which gives me an overall factor of +1. So these 2 operators commute. And if we work out what their products are, it turns out that on this side we get -y tensor y, and on this side we get +y tensor y. So what do these two inference trees tell us? Well, if we follow the assigned values of the trees, we notice that ZZ has to be the product of the value assigned to ZZ has to be the product of the values assigned to these two. The value assigned to XX has to be the product of the values assigned to these two. So the value assigned up here at the root has to be just the product of the values assigned to the leaves. So this means that minus YY, the value assigned to minus YY has to be the product of the values here, and the value assigned to plus YY has to be the product of the values here. But this is a problem, because if you look, these bottom two layers contain the same four operators each. So what we've inferred is that the value assigned to plus YY and the value assigned to minus YY have to be the same. But since those values are plus or minus 1, this is a contradiction. And hence, the set S is contextual, because no matter how I assign plus minus 1s to these trees, I'm going to have to violate some one of the inference relations in one of them. Any questions about this? Okay, feel free to jump in if you think of things as I keep going. I want to just first address one misconception that is often one of the first things that people ask about. So I've said that a non-contextual set of observables should permit consistent joint value assignments. But that does not mean that the joint value assignments that we assign have to be physically realizable. So we're used to talking about commuting sets of observables as those that can have definite values simultaneously, meaning they have joint eigenstates. So that's always true if observables commute. But with contextuality, we're broadening our notion a little bit, where we're not asking if there exists a joint eigenstate of the observables. We're just asking whether we cause some logical contradiction if we assign joint values to them. So if there is a joint eigenstate for the observables, then that state actually physically realizes a set of joint values for them. So in that case, the set has to be non-contextual. There can't be any contradiction because we can physically create the joint values. So commuting implies non-contextual, but the implication does not necessarily go back the other direction. I hope that's clear. Okay, so this brings us to the main result from this first paper, which is an if and only if condition for contextuality for an arbitrary set of Pauli operators. And I'm unfortunately don't have time to go through the proof, so I'm just going to tell you about this result. And we're actually going to be focusing on the non-contextual case going forward. So that's kind of the classical case where we can build these models. So the condition is this: if S is non-contextual, which you should think of as classical, if and only if it has this form. So what's going on here? Well, first of all, there's allowed to be this subset C of S such that every operator in C commutes with all of the other operators in S. So this is just kind of a fully commuting part. And then in the remainder of S, whatever's left over, which we can call T, commutation is an equivalence relation, if and only if S is non-contextual. So in other words, T breaks up into a collection of disjoint subsets that are equivalence classes of commutation. So everything within the subset commutes and pairs from different subsets anti-commute. So non-contextual sets of Pauli operators are exactly those with this form. And let's look at a couple of examples. As we said, any commuting set is non-contextual. So we can think of that as the case when there's no subset T, there's just this, S is entirely composed of this subset C of operators that commute with everything. But also any anti-commuting set is non-contextual. Why is that? Well, you can think of as a special case when there's no subset C, there's just this subset T. And why is commutation an equivalence relation? Well, there's no commutation if everything anti-commutes. So we can think of each operator in S as being its own little equivalence class of commutation. in the case when they fully anti-commute. So that also satisfies this form. And then more generally, any set where commutation is an equivalence relation, which actually includes both of these cases, we can think of this as the case when there's no subset C more generally, but even if the equivalence classes have size larger than 1. So here's an example of that. If my whole set is S enclosed by these curly braces, then the equivalence classes are these enclosed by the parentheses. So if you look here, you can check that each operator, the pairs within parentheses do commute with each other, but any pair from different parentheses, sets of parentheses here, anti-commute. So these are the 3 equivalence classes of commutation within this set. Great. So as a corollary, since the quantum part of a VQE algorithm is just measuring the set of Pauli terms in the Hamiltonian, we define contextuality for Hamiltonians and contextuality for VQE to just piggyback on the definition for sets of Pauli operators. So we say that a Hamiltonian or the associated VQE instance is non-contextual if and only if the set of Pauli terms in the Hamiltonian is non-contextual. Good. Okay, so now let's move on to talking about what happens, what the implications are when a Hamiltonian is non-contextual. So if we find that our Hamiltonian for whatever VQE algorithm we're trying to run is non-contextual, we should expect that we can replace the quantum part of the algorithm by some classical hidden variable model of the kind that we were talking about before. If you remember, that's the goal that we originally set, was to be able to construct such a model. So if we don't find a contradiction, meaning it's non-contextual, then we should be able to actually build the model. And if you remember, this will consist of joint value assignments that are like phase space points, and then some probability distributions, which you can think of as replacing quantum states. So it turns out that we can explicitly construct such a model, and that's, again, pretty, at least for me, fun in its own right, but I'm not going to go into the details because I want to get to later stuff. But the key feature that I want to highlight is that it turns out that the probability distributions in the model can be parameterized by some set of parameters that I'll denote A. And there are at most 2n plus 1 real parameters contained in this vector A for an n, this is for an n qubit VQE. And we should have in our mind to compare this to the order 2 to the n parameters that would be required to denote some quantum state in general. So we have an exponential reduction in the number of parameters here. And it turns out that we can explicitly express the expectation value of the Hamiltonian as a function of the probability distributions, which we can translate just into a function directly of the parameters A. So we're going to generate some explicit classical function E for the expectation value of the Hamiltonian as a function of these parameters. And if you remember from before, well, I've belabored it. But the quantum part of VQE is just estimating this expectation value. So we now have an explicit function for the expectation value, which we can just use to replace the quantum part of VQE. So now we have this variational eigensolver with the quantum part crossed out. So what we've obtained is a classical variational estimator for the ground state energy in the non-contextual case. So in other words, we've taken something that looked like a quantum problem. We started with this quantum Hamiltonian, and we've translated it into a classical estimation procedure, which amounts to showing that there really wasn't, at least in this sense, anything explicitly quantum going on in this algorithm in the first place. Okay. Okay, I'm getting towards the end here, and I'm also running out of time, so I'm going to move right along. So we've been talking for a while now about when a Hamiltonian is non-contextual and what we can do in that case. But what if the given Hamiltonian for a VQE is contextual? Well, we know that in that case, we can't build a classical model for the full Hamiltonian, because that's exactly what contextual means. But we could imagine partitioning the Hamiltonian into a non-contextual part. So this is just some subset of the terms together with their coefficients, and a contextual part, which is whatever part is left over. So in general, this would be contextual. Might not be, but we'll call it H sub C to cover the general case. And then we could use, well, we could choose the non-contextual part to be as large as possible according to some norm of our choice. And then we could use our classical method to approximate the ground state energy of just the non-contextual part. And we could take that to be an approximation to the ground state energy of the full Hamiltonian and see how well we do. And it turns out that we did try this for a lot of molecular Hamiltonians, and it works okay. It kind of gets into the right ballpark, but it's generally not accurate enough to be useful. And I'll show you those results in a couple slides. But for now, let's consider how we might do better. So let's refer to the energy minimizing parameter setting for the non-contextual part. So remember, the non-contextual part gives us some set of parameters A.
Well, maybe I could just stop with a question here.
Yeah, sure.
So this division into non-contextual and contextual looks to me like it's a bit fuzzy, because I think, and you correct me if I'm wrong, if I were to make a mistake and leave some non-contextual part in the contextual part, no errors would necessarily arise. It would just be that I might not have the most efficient breakdown that you're trying to achieve here.
That's right.
And am I correct in that?
You're all right in that. So this is, yeah, I'm sweeping it under the rug a little bit, but doing this partition is an optimization problem in its own right.
Okay, good. And perhaps not unique, I would think, as well.
It's not unique. And in fact, it's NP hard. So I'll show you some numerical results in a couple slides. We just used a greedy algorithm to do this. And there's definitely room for trying to optimize it. But we shouldn't expect to be able to find the actually optimal non-contextual part efficiently in worst cases.
Okay.
Yeah.
And we have to define what we mean by optimal, I think, at some point. As
right,
well.
right. I think pretty much any way that you mean, pretty much anything that you mean by optimal, this problem is going to be, pretty much anything that you mean by optimal within reason, this problem is going to be NP hard.
Okay.
Yeah.
I'll come back with some thoughts near the end.
That would be great. Yeah. This is something that there's definitely room to do more work on to try to make this decomposition work better. Right. So we're going to do our classical imagine doing our classical optimization just on the non-contextual part here. And that gives us some parameter setting that minimizes the energy of the non-contextual part. Well, it turns out that this non-contextual ground state, we can call it the ground state, even though it's a parameter setting, corresponds to some subspace of quantum states. And in particular, it turns out that we can derive a set of commuting operators that I denote by the script A, such that the non-contextual ground state corresponds to their common eigenspace. And we can actually derive the eigenvalues that we would assign to get that eigenspace as well from the non-contextual ground state. So what we can do is try to obtain a contextual correction to the non-contextual approximation by minimizing the energy of this contextual part, the leftover terms, within this common eigenspace that corresponds to the non-contextual ground state. And we would do this using an actual quantum VQE algorithm whose ansatz is just restricted to this subspace. So that idea is summarized here on this slide. We're assembling the expectation value for the full Hamiltonian out of a non-contextual contribution that's estimated classically, and then a contextual correction that we estimate on the quantum computer. And it turns out that, I'm going to try to move really quickly, so I might not explain everything that's on this slide, but this subspace, when I restrict the contextual part to this subspace, it becomes simpler. And in particular, it becomes a Hamiltonian on fewer qubits. So if I start with n qubits, and then I force myself to be restricted to a subspace of the operators in A, assuming these are like Pauli operators, then I remove 1 qubit for each operator in A. So this Hamiltonian becomes smaller. And here's an example of that. I can come back to that if people want to, but I'm gonna keep moving. So what we could try then, well, first of all, we can just see how well this works, and hopefully we can get a better approximation by doing this method. It's mostly heuristic, but we can just try it and see how well it works. But then we might ask, well, what if I have this smaller Hamiltonian that I'm doing the simulation on my quantum computer on for the contextual correction? What if my quantum computer actually has a few more qubits than I need here? Well, one thing we could try is to just stop restricting to the eigenspace of some of the operators in A. If I reduce the size of A, then I will increase the size of the quantum search space for this contextual correction part of my algorithm. And in particular, I can reduce the size of A to increase this number until it's exactly the number of qubits that I have access to on whatever quantum computer I actually have. And this is kind of a nice feature because, you know, the way quantum computers are now, every additional qubit we have is kind of a precious resource. So we really want to be able to exploit all of that as far as we can. So this lets us do that. And again, this method is mostly heuristic, so we don't have a general characterization of how well it will work, but we can try it. So here's a bunch of example applications to molecules, and this is my last real slide. So let me just quickly talk about this. So what's going on here? Each curve in each of these plots corresponds to a particular atom or molecule. The leftmost point in each curve in the 0 qubits column, sorry, the x-axis is the number of qubits that are being used on the quantum computer. So for the quantum part of the algorithm. And the y-axis is the resulting overall error in Hartree. So on the leftmost point in each curve, I'm using 0 qubits. So these leftmost points are the pure non-contextual approximation, where I'm approximating the total ground state energy as just the ground state energy of the non-contextual part. And then as I move to the right, I'm using more and more qubits on the quantum computer for the contextual correction part. And we see the arrows go down until we get to the rightmost point in each curve, which is when we're not enforcing the non-contextual ground state at all anymore. So these rightmost points correspond to doing full VQE, so the full Hamiltonian, which in principle gives us 0 error since we can search the whole space. And so the nice feature here is that we find that we're achieving pretty good accuracy even before we're using the full number of qubits. So these black lines correspond to chemical accuracy, which roughly speaking is the accuracy that we would need in our ground state energy estimate in order for it to be useful for doing chemistry calculations. And what we see in almost all of these plots is that we're getting to chemical accuracy before we're using all of the qubits that would be required for full VQE. So the hope is that we can use this method to simulate larger molecules on smaller quantum computers while still getting usefully accurate results. I should say that the quantum parts of these plots were simulated classically, which is exponentially costly, but these examples aren't too big. So let me just quickly summarize what we've done. There's 3 main pieces here. First of all, if you give me some Hamiltonian that you want to do VQE on, we can determine whether it's contextual using the if and only if condition that we talked about. If it's non-contextual, then we can do this classical simulation method where we construct the hidden variable model and then just simulate using that. And if it's contextual, we can do this partitioning into the non-contextual part and the contextual part. And yeah, we can trade off quantum resources for accuracy, I've said here. So we can use all of the qubits that we have access to try to get better accuracy in this estimate. So thank you. Sorry for running a little bit longer than I meant to. Here's links for these, and I'm happy to answer more questions.
Thanks, Will. We do have a question in the chat. I don't know if you can see that.
I might be able to open it.
Okay.
Actually, I'm not sure how to open it in this view, so maybe you can read it.
Is this a normal product? But it pertains to something you were discussing sometime earlier, about midway in your talk.
Yeah.
Is this a normal product was the question. I'm not sure.
Actually, if you can go back to the three figures, in that you have the IZ and CI. So I just wondering when you
This picture,
like where you had YY and the yes. So in this figure, multiply when you say that this is the product of CI and IZ, you mean that as a normal product and
yes,
not a Kronecker product, right?
that's correct. Just
Okay.
yeah, just a normal operator product.
Yeah.
Yeah.
Okay.
Yeah. Good.
Okay. Yeah. That's what.
Yeah. Each of the the key feature of these trees is that each parent node, for each parent node, the children commute, and the parent node is the normal operator product of the children. So that's the feature that these trees have to satisfy in order to be proper inferences. Good question.
Okay. Thank you.
So I would have some comments. I actually will. This is the first time I get a bit of an understanding, I think, of what you've been doing.
Mm-hmm.
I see a lot of consistency between what you're saying and what we achieve, what we seek to achieve when we do something like basis light front quantization or ab initio nuclear structure theory, working in a basis function representation. Because when we define a basis, we always try to pick a basis with a maximal set of commuting observables.
Mm-hmm.
The maximum number of operators we can identify, which we know from space-time symmetries and other conservation rules, should commute with the Hamiltonian and commute with each other. So this is an attempt at the basis function level to isolate I think the classicality from the non-classicality in your way of talking.
What function is that? Yeah.
Yeah, if we can break the space up into subspaces of the form where each subspace has some set of quantum numbers corresponding to the commuting observables. These are your classical markers, if you like,
Mm-hmm.
for the problem.
Mm-hmm.
In reality,
and then in some sense, you're doing this kind of partitioning in a similar way. You have kind of a classical part of the problem with this commuting part, and that block diagonalizes your Hamiltonian, and then each block is kind of a contextual. Well, in general, it would for sure be contextual. Yeah. Right.
Exactly. That's the way we think about it, or can think about it.
Mm-hmm.
And so then the challenge is still to deal with any subblock where it's purely contextual in your language within a subblock.
Mm-hmm.
Now you have all your contextuality left over that still has to be dealt with.
Right.
And
so there's a slight distinction to be drawn here, I think, because non-contextuality is a somewhat broader notion than commutativity. What you're doing if you sort of block diagonalize a Hamiltonian by identifying operators that commute with it, falls into this category, but the hope would be, well, the distinction is, if you can identify some set of operators that is non-contextual, they wouldn't necessarily even have to all commute. So you could actually do a similar kind of process, but maybe with a larger set of observables because they're not restricted to necessarily commute. They just have to satisfy this this form where they partition into a commuting part and a part where commutation is an equivalence relation. Now the caveat to that is that there's no known way to identify non-contextuality for arbitrary sets of observables. This condition only applies to sets of Pauli operators, which have a pretty nice algebraic structure, maybe nice is in the eye of the beholder, but it's at least quite restricted. If you're looking at general observables, it's actually not. I mean, the condition is well understood, but just actually evaluating it given some set of observables is believed to be a hard problem. So, yeah.
To my mind, having these demonstration proofs and so forth is valuable because it helps codify the discussions, and there's a big but in my mind, and that is that in the real world, I have a Hamiltonian that I think I know from some underlying theory, and I believe I know the symmetries which define a set of commuting observables, and going from there to a useful split between classicality and non-classicality is still a big jump, I think.
No, I think you're right. And this is, I mean, what you're kind of roughly describing is something that's an ongoing part of our research, which is trying to sort of push this definition that currently only applies to Pauli operators, push it out as far as we can into other kinds of Hamiltonian decompositions, other kinds of observables that aren't just Pauli operators. It's kind of convenient for us that VQE is almost always done with Pauli decompositions because Pauli decompositions are relatively simple to work with. So we can work out these proofs without too much difficulty. But as you say, in the general case, this can be a lot harder. And even if you do identify some non-contextual set of observables, trying to understand what you can do with that in the general case also is potentially a hard problem. This is kind of speculative because we really non-contextuality and contextuality in these more general cases, the definitions are well understood, but the actual structures that crop up are not.
Okay. Let me open it up again to others who may have questions.
So I have a question. Since you mentioned that it is a NP hard problem, do you think that you can actually use, like in the future, you could actually use a quantum algorithm to first partition the Hamiltonian into a non-contextual and a contextual part to begin with?
I love the question. I mean, the short answer is I don't know. So the question is basically there are quantum algorithms for trying to estimate or approximate solutions to NP-hard problems or optimal solutions to NP-hard optimization problems. Could we use such an algorithm to do this partitioning? So in some sense, this would be using a quantum algorithm to do compilation for another quantum algorithm. I don't know. The algorithms for, I think the main caveat, the main thing I would worry about with that is that we don't actually know that the quantum algorithms for NP-hard problems work. And there's strong evidence to think that they don't work in worst cases. Whether they can give you better approximation ratios, to the best of my knowledge, is not really known. So there's a bunch of question marks there. in the field more generally about just solving NP hard problems with quantum computers. But it's a great idea. I mean, it's a very aesthetically appealing idea in some sense, but I really don't know whether it will work.
Will, maybe
you.
I could suggest, if I could suggest you turn off screen sharing here
Yeah,
so
sure.
you can read the chat, because there's
Oh, there's several
at
questions
least
in
a
it.
two-part question, maybe a three-part question in that Bo Basili has.
Okay, Bo has asked this. Let me look very quickly.
Well, so
How much does achieving, sorry, what?
yeah, it's basically just the same question, just me rephrasing it multiple times. Go ahead.
How much does achieving chemical accuracy depend on how you split the Hamiltonian into the non-contextual part? Good question. It depends a lot. So if you remember in these plots, the initial non-contextual approximation is not that great. That is before we use any quantum correction. Let me just share again. Now that I've seen the question. Whoops. Yeah. So these initial non-contextual approximations are in the 0 qubits column. So they're all outside chemical accuracy. The greedy algorithm that we used, actually, we tried a bunch of different heuristics for doing this partitioning into the non-contextual part and the contextual part. And this one actually worked the best, just kind of the naive first thing that we tried. Turned out to work the best out of everything we came up with. And in some of the small cases where we were able to just do a brute force search to find the optimal solution for that partition, it actually did find the optimal solution. How much does it depend on whether you found the optimal solution? What I can tell you about that is that for the other heuristics that we tried, the errors that would have appeared in this 0 column were much, much worse. So a lot further outside chemical accuracy to start with. I would imagine that when we apply this whole procedure where we're starting to add in the quantum correction part to it, the errors would go down, and the plots would I think would look roughly similar. They would just start out at worse errors. Does that answer your question?
Yeah, and sort of an extension. Would any of that difference? Do you think, is there any suggestion that it would have any correlation to the certain structures that a system that the system you're modeling has? Like say I don't know, you've got a particular like a strong, like a halo structure or something. As far as how the thing the quantum system you're actually modeling, does it seem like this could be good for certain specific kinds of systems, but not other systems? Or is that just?
No, that's a good question. And I think it definitely does. We're actually in the process of writing a paper about this. So you're spot on, or at least trying to write a paper about this anyway. Yeah, you're pretty much spot on. First thing to say about this is that I'm not showing in these plots some of the Hamiltonians that are just entirely non-contextual. So there's no partitioning to be done. The whole Hamiltonian is non-contextual. And it turns out that a few things in sort of minimal bases, small atoms, small molecules turn out to be like this. H2 in the minimal basis is just non-contextual already. But then also a few of the noble gas Hamiltonians turn out to be non-contextual at the beginning. So their plots in here would just look like sitting down here at 0 error all the way across, even when we're not using any quantum correction, which is why I didn't put them in. They're not particularly interesting on these plots. And why that's true, we don't really understand. In terms of performance within these ones that are non-contextual, we have a really wide range in performance. Like amongst these 16 qubit Hamiltonians, sodium hydride doesn't reach chemical accuracy until we're using 14 out of 16 qubits. But HCl reaches chemical accuracy when we're using 4 qubits out of 16 qubits. And I would imagine, or I kind of at least hope, that this is reflecting something about sort of the chemical structure that's more contextual for sodium hydride than it is for HCl. So there's something going on here that requires more quantum resources to capture. And it would be really, really cool to try to be able to understand this at the chemistry level, because then we have this sort of concept of contextuality that's coming from foundational theory that's informing something that we may only have kind of higher level descriptions of in at sort of the chemistry level. So I would love to see that. We have some kind of mixed results, but unfortunately, a general characterization of that kind has so far been elusive, but I would love to see that. Does that answer the question you were asking?
Yeah, yeah.
Okay, yeah.
So
I think it's a natural question to ask and a really good one.
So I have another question. Is it fair to characterize the point, which is at 1 qubit, relative to the point at 0 qubit, as approximately the result of lowest order perturbation theory? Or is that distinct from that?
It's distinct from that, although there are some qualitative similarities. The main distinction is that there's really no general characterization of the size of the contextual correction. So there's no guarantee at all that this expectation value of the contextual part will be small compared to the expectation value of the non-contextual part.
No,
yeah.
but that's a little bit different from what I was asking, because whatever it is, it can be small or large. It's still the answer. It could still be the answer of lowest order perturbation theory. The theory may not be well converged, but it could be an answer approximating what you would get from lowest order perturbation theory.
I think if we want to try to draw the analogy to perturbation theory, I think some kind of degenerate perturbation theory is probably the thing that looks most similar.
Yeah, because you're.
But I don't know of a sense in which
you're allowing the amplitude itself to change, and that's the distinction from ordinary lowest order perturbation theory. The ordinary lowest order perturbation theory takes a frozen approximation for the amplitude and calculates an estimated correction, but you have something more dynamical,
right? Which
is like, as you said, more like degenerate perturbation theory.
Yeah, we have this subspace that we're doing the correction within.
Correct. Yeah,
I think it's fair to draw an analogy to degenerate perturbation theory. I think actually formally, like casting one as the other or vice versa, I'm not sure how to do that.
Mm-hmm. On your scale, though, it would be in principle possible to put a bar on the 0-bit point, which measures the first order perturbation theory correction, which might be an indicator of some sense of the change from the 0-bit to the 1-bit step.
Yeah, I don't know whether it would be. Yeah, I don't know, basically.
You'd be curious to an outsider to see the contribution of first order perturbation theory. That would be just.
That would be interesting. I don't know whether it will correspond to the 1 qubit piece. I don't. So what's happening as we're going across here and adding more qubits is we're just increasing the size of the subspace.
Correct. Yeah.
I don't know. So I don't know how that matches to.
It'd be interesting. All right.
Perturbation theory, but I'm not an expert in perturbation theory, so I'm not sure.
Good. Very good. Great. And I don't see any more questions in the chat box. So if we're last call for last questions to Will. He's reachable by email, I
I
assume.
am. Please,
Yeah.
please do
And,
email me if you have anything else.
We'd greatly appreciate if you could share your slides by sending
Oh
them.
yeah, sure.
That would be great.
Yeah, definitely.
Often we think of our questions the next day.
Yeah, please do email me if you have any other questions or comments.
Great. Thank you very much, Will, for this